Hello, this is the Efreeti processor, and to begin with, we will show you how we start a simulation and describe how the programs and data are loaded. And then we will have a brief discussion of the caches. So to start with, we have a test program that sends the information into the CPU, which is our overarching encapsulation of all the modules. So it has pretty basic signals, and it has the instruction registers and the register values and the ALU output as our data we're attempting to verify. So in order to begin it, we click it, simulate, start simulation. Alright, we add the signals to the waveform. Make sure we have it for about 1,000 nanoseconds. We run. And then we can verify that the program has loaded appropriately by looking at the instruction registers. Change the radix to hexadecimal. So we can see that the program loads as it should, and that the instructions propagate. So 2002 moves forward through the pipeline, and it is loaded by sending the name of the file that contains all the bits, and those are then loaded into the memory, and then the memory handles them appropriately.
We configure the cache with two parameters. One is cache miss penalty, and another is miss ratio. And so based on such two parameters, we can configure the cache performance.
Okay, for one moment, let's show in the generic memory module. It's part of the two parameters that go into the module is the miss rate. And then there's also the seeds to initialize the random generator.
Yeah, and we use a random number generator to simulate the cache miss. We cite just what we cite. We have one parameter named the miss ratio. We generate some random number, and if such random number is below such miss ratio, we think there is some cache miss. So based on such random number, we can simulate the cache miss.
Now, the next part of the presentation would ideally involve us demonstrating how our processor beautifully and flawlessly executes programs. Unfortunately, there are a few bugs left in our VHDL that are preventing us from successfully running programs, but we can still talk about what would happen if those programs could run. So,
did you show your hazard detection and the code?
Your hazard detection is VHDL, mine's
Talk
all
about mine. Okay.
similar.
Alright, so to demonstrate how we handle the hazard detection, in the state machine we instantiate a module that acts as a forwarding manager that feeds information into the ALU. So if we look at the forwarding manager, it takes in all the forwarded signals. So it takes in signals from the EX stage, which is the current stage. It takes signals in from the MEM stage, which is the next stage. And then it takes signals from the write back stage, which is 2 stages into the future. And then it has 2 outputs to the ALU. And it first determines what types of opcodes they are. So the memory and write back can have no store, so then it would just ignore the feedback because no data was stored, or it could have one store, which means it stored a value to a register, which means it could be used to forward its data. And then the EXE stage, or the EX stage, has 3 different types. So if it reads from no registers, then it can also ignore this whole forwarding process. If it reads from 1 register, then it only checks against the 1 register to see if they match up. If it reads from 2 registers, then it checks against both registers. So then we use ifs to determine what type of ops are in each stage, and then based on this we determine what kind of forwarding is required, and we of course prioritize the newer information. So the next stage is going to overwrite the write back stage, but if there's nothing else, then the write back stage might have the more current data.
And the other way that we deal with hazards is, in many cases, we notice that if you insert a no-op after branches, then as everything propagates through the pipeline, it nicely resolves itself. This isn't necessary if we have both threads running, as we use fine-grained multi-threading, and the instruction from the other thread takes care of, or it effectively acts as a no-op in thread of the branch. So what we do is, at the assembler level, we put no-ops in after branches, and then at runtime we check if both threads are running, and if both threads are currently active, unstalled, have programs, etc., we just skip over the no-ops and continue. And since this is the only way that a no-op would get into one of our programs, this doesn't cause any problems. But if for some reason you wanted to insert no-ops manually, you could just insert 2, it would remove the first one, and you're fine.
But at this point, the user has no way of inserting the no-ops anyways, and because if both threads are running and the machine's behaving in ideal conditions, we have forwarding and branch detection that prevents any need for no-ops, because there's only a one instruction window where there would be a hazard. So if there is a hazard, the assembly has already inserted that no-op and we don't remove it. But if both threads are running as we would like them to be, then the no-op is skipped over, so it runs in optimal conditions. So it runs optimally in both situations.
Now, we obviously can't run instances of programs and measure their performance, but we can talk a little bit about how we would expect the relative performance, the performance of one instance of a program running versus 2 in parallel. And because, as we've mentioned, having both threads running in parallel lets us remove some no-ops, we should get a higher throughput of instructions, but without actually being able to test it, there's some concern that delays caused by having to dealing with flushing out the pipeline in the case of cache misses may prevent us from actually seeing significant performance increase. It's something we'll definitely test when we get it running, but
it depends heavily upon the cache behavior, because if the cache behavior is operating in such a fashion that the cache misses don't happen very often, then both programs running, or the penalty is extremely low, then both programs running is our ideal situation. So it should be able to mitigate any losses we might suffer from having more cache misses.
The division of labor in our group, each one of us, there was a lot of overlap and help with debugging and such, but each one of us tended to focus on one area. Greg handled the kind of overarching logic, the state machine, that kind of stuff. Yang focused on the memory and registers, and I did all of the assembler work and dealt with
managing the instruction formats.
Managing the instruction formats and all of this kind of stuff.
And the ALUs.
The ALU.
Right.
So actually operating a given, or performing a given instruction.
So you handle the operations in many facets. Alright, is that?
Yep.